Good, perfect. All right, so this is the first real lecture. I want to start off with Russell's paradox. So my brother and I have worked out most of our issues now that we no longer live under the same house. But he's an engineer. And so he and I see the world very differently. We actually have a little dictionary when we want to talk about things like the Fourier transform, because he'll say things one way, I'll say things another. What's the square root of -1? If you're an engineer, what do you say? You say J. So there's slightly different languages, and it can take a while to go back and forth. One of the things he doesn't understand is why we mathematicians obsess so much about proofs. Because all these cases you're worried about, they never arise in the real world. You're focusing on things that just don't arise. How many of you went to Ken Ono's colloquium earlier this week? So he gave some really nice clips and talks about the upcoming movie on Ramanujan, where he was one of the consultants, and trying to convey to a cinematic audience, we can't say movie, a cinematic audience, why mathematicians obsess about proofs so much. Why do we care so much about stuff like this when these things are just obvious, and isn't it clearly the case? So what I want to do is I want to show you Russell's paradox. Hopefully, of course, you've all read the book, so nothing I'm going to do is going to be that surprising. But in case you just happen to forget what you read, hopefully this will be a little bit shocking. Or if you're new to the class. So what is a set? So, we do have a couple of people in the tennis team here, but if you don't ask them, if you ask a mathematician, what is a set? They'll basically say something like, it's a collection of objects, maybe a collection of objects that have a certain property. So a natural idea is, let me gather all things that have a given property together. So maybe P is going to be the set of all objects with a property P. And I'll use a script P here to highlight that it's coming from this property P. And then you give me different properties, different collections of objects will then be created. And so the question is, can you form sets like this? And so Russell considered the following. Let's let R be the set of all x such that x is not an element of x. Can somebody give me a natural number? 1 with an M&M. Is 1 an element of 1? No. Most things are not elements of themselves. So do we expect many things to have this property? Yeah, I would expect most things are not going to be elements of themselves. Okay? So there's a natural question. Is this a set? Let's assume yes. Well, if it's a set, we would like to figure out what are the elements of this set. The natural numbers are not a natural number, so the natural numbers would come in here. So there's two possibilities. Let's consider x equals r. So whenever you want to analyze something, you always want to choose a good value to analyze. The only thing that I've really written on the board is this script set r. So let's consider x equals r. That's a really good choice for x. So case 1, and this is fun as a Bostonian, r is in r. And case 2, r is not in r. Okay? If r is in r, what does that mean? R is not in r. R is the collection of all things that are not elements of themselves. So remember, r equals the set of all x. X is not an x. So thus, r is not in r, as r is all things not elements of self. I'm sorry, right. All right, so we know if r is in r, r is not in r. Contradiction. Therefore, case 2 must be true, and it must be the case that R is not an R. Now, I've talked briefly that one of the most important results we have in probability is the law of complementary probability. If you know the odds that something happens, you know the odds that it didn't happen. It's just 1 minus that. So if you want to calculate some events, sometimes it's easy to calculate the probability that it doesn't happen. Somebody came to my office yesterday checking some of the homework, which I encourage you to do. Rather than doing all the different die rolls and stopping and not doing the last one and saying, well, whatever the last one is has to be 1 minus the other probabilities, they actually calculated all of them and noticed that things didn't sum to 1, that they must have made an error somewhere. It's a great way to check your work. So let's check and see what happens if we analyze R is not an R. Well, if R is not an R, what does this mean? R is an R. Thus, R is an R by definition of R. What can you deduce from this? What do we deduce from this? What lesson?
R is not a value.
So 1, R is not a set. 2, take a course in set theory. The subject is much harder and much more subtle than you would expect. This one example destroyed the edifice of set theory. I believe Russell came up with this when he was a grad student and sent this to Frege, who was in the middle of writing the great volume of the foundations of set theory. Since this is being recorded, I will not say exactly what Frege said when he got the letter. You could probably figure out which phrase this is. Or maybe you have to figure out what language he was speaking to figure out which version of the phrase. But in great kudos to the mathematics community, this was not hushed up. There was no hit put on Russell. This wasn't suppressed. This led to a reformulation of set theory. And how do we deal with something like this? And beautiful theory called Russell's theory of types to deal with stuff like this. You have to put things on a rigorous foundation. We are not going to worry too much about this. It would be wonderful if everybody could take a class in measure theory by Friday and master all the material, and then we could really go to the basics. We're not going to do that. But I want you to be aware of the difficulties. So what I'm going to do is I'm not going to assign probabilities to every possible event, partly because we can't. What we will do is we will assign probabilities to events that for the most part are all we need for what we want to do in the real world. Okay? So how many of you have heard of the Banach-Toski paradox? Basically it says you can take a solid sphere and chop it up into 5 pieces. And you can rotate and translate 3 of the pieces and rotate and translate 2 of the other pieces. These pieces are disjoint, and when you put them back together, you have 2 copies of your original sphere. Should your volume change if you rotate? No, that's a very reasonable assumption. Volume is invariant under rotations. Should it change if I translate? Should I be able to cut up the sphere and get 2 spheres? If you don't want to do it with a sphere, do it with either, a stack of $100 bills. And you can basically just double your money. Now, if you want to actually do this in the real world, if you actually want to do these 5 cuts, these cuts require something called the uncountable axiom of choice. I do not like the uncountable axiom of choice. This is one of the few times I can actually be philosophical in this class. I believe it gives too much power to mathematicians. God, I have no problem with God using the uncountable axiom of choice. For us mortals, no. Now, some of my colleagues feel very differently. Huge subjects of mathematics need the uncountable axiom of choice to really get started. The whole point comes down to when can you do things. It turns out that the sets you need, the cuts you need, are so bad they cannot be described in a nice way that you can visualize. So there's no danger of this actually happening in the real world. But what it means is our notion of what is a volume, it depends on our notion of sets. So I want to, for the most part, skip a lot of the technical stuff. It's in the book. You can read that. I want to give you a brief flavor of what's out there. So I want to talk briefly about 3 keywords: finite, countable, uncountable. All right. Can somebody define finite for me? It's not infinite. Can somebody define infinite for me? All right. Let's not go around in circles. Yes?
If it's infinite, then you can, or I guess if it's finite, then you can create a,
I'm not trying to be a smart ass. It's not that I haven't prepared my lecture for today. It's actually non-trivial to define what it means to be finite and infinite. So one thing we can say is a set has n elements if can place in one-to-one correspondence with the set 1, 2, ... n. And so this is my A1, this is my A2, this is my AN. Every element in my set A is associated to one of the elements from 1 to n, and vice versa. I'm not going to go into too much detail. I'm pretty sure you all have a good understanding of what finite is. Okay? But this is really how you need to define it in set theory. You have to have a rigorous notion. And then infinite is going to be not finite, yes. So infinite basically just means you can't put it into a one-to-one correspondence with any finite set, with any set from 1 to n. Just to see how bad things get, the number 0 is basically put into correspondence with the empty set. The number 1 is put into correspondence with the set containing the empty set. The number 2 is put into correspondence with the set containing two elements, the empty set and the set containing the empty set. And I'll just do one more. 3 is put into correspondence with the set containing the empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. I think I need one more grace. This is a subset of this. Both of these are subsets of this. All three of these are subsets of this. So the notion of less than is actually the same as inclusion. This is how you can rigorously define things like the integers and go through stuff like this. So whenever you get to a proof this semester that you're not enjoying, think of how bad it could have been. Right? I'm not doing stuff like this. You have to leave me something later in the semester. Okay? So I'm going to assume now that we're all comfortable with finite sets and something along these lines. And something is going to be infinite if I can't put it into a one-to-one correspondence. So there's going to be two types of infinities. There's going to be the countable infinities and the uncountable infinities. So an infinite set is countable if can place in a one-to-one correspondence with the natural numbers. Instead of the natural numbers, it turns out I could also do the integers. I could also do the rationals. Any two countable sets, I can use any one of them as my basis. And what this basically means is here I have A1, A2, A3 going off and off and off like this. Okay, so it turns out the integers are countable. The rational numbers are countable. For our purposes, we're only really going to need to deal with countable sets that are essentially either the integers or the natural numbers. And we may or may not include 0 as a natural number depending on what problem we're looking at. Okay, so this is the prototypical countable set. The difficulty with the uncountable sets, we go through this in the book, things break down. And the whole point about a countable set is there's a one-to-one correspondence. So if you want to know when you're going to reach something, you know. I know how long it will take me to reach a certain element. It'll be in the 2,314,000th step. Turns out unions of countable sets are countable. Countable unions of countable sets are countable. Power sets of countable sets are not countable. And so, I almost got out. All right. So what I want to do now is I want to go and talk a little bit about uncountable sets. Not too much, but just a little bit. So we have the natural numbers 0, 1, 2, 3, ... And what you can do is you can look at sequences. And so we can look, for real numbers, I can look at the interval 0, 1. So this is going to be all x between 0 and 1. And I can write it in binary. So point 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 0, 1. That would be some binary number. And essentially, one way to view this is at each point, I either take a number or I don't. I either have a 1 or I don't. So this would be equal to 0 times 1/2 plus 0 times 1/4 plus 1 times 1/8 plus 1 times 1/16. That would be this number. So roughly what's going on is for each of my integers, I either take the corresponding term 1 over 2 to the n or I don't. And so in some sense, the size of 0, 1 is 2 to the size of the natural numbers. And so we use aleph naught, the Hebrew letter, to be the size of the natural numbers. It is the smallest infinity. Okay? This is going to be a larger infinity. So this is a big theorem. It's called the power set theorem. If you have a set, the power set is larger than the set. So again, today's just a crash course in set theory. So power set of A is all subsets of A. So for example, if A equals 1, 2, 3, the power set of A, well, it could be the empty set. I could have just 1, just 2, just 3. Then I could have just 1 and 2, just 1 and 3, just 2 and 3. And then I could, of course, have everything. All right. How many elements do I have in the power set of A here? 8. There's a better way to say 8. 2 cubed, right? So here, the power set of A, the size of that is equal to 2 to the size of A. This must be true because we've proven it, we've checked it for one case. So you would now rigorously prove this, that if you have a finite set, the number of subsets of A is equal to 2 to the A. One nice way to look at this is for each element of A, if I'm looking at a possible subset, I either take the element or I don't. So for each element, I have 2 possibilities. I take it or I don't, I take it or I don't, I take it or I don't. 2 times 2 times 2 is 8. And that's essentially what we're doing over here when we're talking about the size of the interval 0, 1. It's 2 to the natural number, 2 to the size of the natural numbers. So the continuum hypothesis, which you're supposed to look up as one of your homework problems, is whether or not this is the second smallest infinity. So the size of the natural number smallest infinity, this is going to be a larger infinity. There's a great proof, Cantor's diagonalization argument, that proves that this is a strictly large infinity. Is there an infinity in between, yes or no? It turns out it's up to you. If mathematics is consistent, it's consistent if you assume that this is the smallest infinity, and it's also consistent if you assume that this is not the smallest infinity. You can take it either way. One of my mathematical grandfathers is Paul Cohen. He was the one who finished the analysis of this very difficult problem. Right? So I don't want to get into too much detail on set theories and whatnot, but I want you to just have at least some sense of what's going on, what the different questions are, what the different quantities are, what we're going to look at. We are not going to talk about uncountable sequences. We will only talk about countable sequences. So now, what kind of sets will we talk about when we do probabilities? So, and I guess I can erase this now. So, we will study intervals, disks, nice regions. So I could give you something like this, and I could ask maybe, what's the area down there? What's going on in that part over here? Okay? So in terms of what I'm allowed to study, I have a lot of freedom in terms of what we describe. Fortunately, looking at just intervals, disks, nice regions, this is going to be enough to allow us to get most of what we care about. And then if you take a measure theory class, what you start to do is say, what if I take a bunch of intervals and I look at unions and intersections of intervals, and I create a new class of sets? Then I can take unions and intersections of those classes of sets. And then I can take unions and intersections of those classes of sets, and I can keep playing this game. And if you like that game, take measure theory at some point. And then you can start talking about a larger, wider class of sets to look at. Any Red Sox fans? What was the score last night? 6-5, excellent. Well, actually it wasn't excellent, we lost, but we don't really need to know that much to talk about the Red Sox scores. It's going to be some integer to another integer. And so if I want to try to figure out what's the probability a given score happened, I'm really not worried about the Sox scoring pi runs. I've really got a nice focus as to what's going on. So for our class, if we just look at intervals and disks and whatnot, any econ people here? What's something the Federal Reserve might be interested in doing? Interest rates. So when the Federal Reserve is looking at interest rates, do you think they're going to look at moving the interest rate in a nice interval, or maybe some kind of intersection of unions of intersections of intervals? No, you're going to have a very nice, well-defined problem. I want the interest rate to be moving in this range. And as it moves in this range, I want to see what happens. So for the events we care about, it's sufficient if we can assign probabilities to stuff like this. Okay? So if you want to know more details about stuff like this, if you want to see the deeper theory, by all means let me know, and I'm happy to talk about stuff like that. But I just want the barest minimum needed for us to have the conversation. And the smallest amount we need is to just get some sense of what the different terms are. So that's why you have a homework problem where I ask you to do some basic things about open set or closed set, a set that's neither, a set that's finite, some kind of stuff in the plane. I just want you roughly familiar with the words. This is not a class where measure theory is used. If you know measure theory, that's wonderful, but I'm not teaching the class as if you know measure theory. Okay, what we should be doing now is we should be talking about probabilities. All right. So, all right, so now we're finally really beginning the class. So we have some outcome space. All right. And what do you think is in the outcome space? Outcomes or events, right? Contains outcomes or events. It's very similar to what we were doing before with the songs I was playing. You can almost guess what the outcome space must contain. Okay. What do you think? What letter do you think we would use to represent outcomes? So if the outcome space is a capital omega, what do you think? Lowercase omega. Often write lowercase omega is an omega. If you make it a W, that's pretty close. But if you're going to be a math major, you should learn the Greek alphabet. Okay? This is one of the few times where I think we do encourage knowledge of the Greek letters on campus. Okay? So omega is the outcome space. Little omega is the events. What we want to do is we want a function, say probability, which maps events to 0, 1. So this is where things get interesting. It's which events are we allowed to talk about. So if we go back to the Banach-Toski paradox, which I have not done in great detail, you can see more in the book. You could look at maybe all the different ways you could cut a sphere into 5 disjoint pieces. And maybe we want to put some kind of probability on choosing one of those cuts, or various things. I don't want to deal with cuts like that. I want to restrict the things I'm looking at. So whenever I'm doing things here, I only want to talk about nice events that I can assign probabilities to. Okay? So in general, given a space, we will only be able to assign probabilities to a subset of that space. There's always one easy thing to do. And nothing else. So I will consider the most trivial possible example. I will only assign probabilities to nothing happens and something happens. What's the probability nothing happens? 0. What's the probability something happens? 1. So in a situation like this, my probability function, the probability of the empty set would be 0. The probability of the whole space would be 1. This is not going to be that useful for doing anything in the real world. I'm going to want to assign probabilities to events. I want to know what's the probability the Red Sox scored 5 runs and the Orioles scored 6. Or maybe a better event is what's the probability the Red Sox scored fewer runs than the Orioles. This year I know it's not worthwhile talking about the probability they scored more. I want to be able to assign probabilities to a large class of events that will be useful. But it's not always going to be the case that I can assign probabilities to every event. So one of the big things to start doing is we can go back to, say, an outcome space that has only finitely many elements. And then in that case, it's not going to be too bad. So let's say omega equals omega 1, omega 2, omega n. And we can let the probability of omega I be pi. So I have some finite collection of objects. Each object is assigned some probability. What probability do you think I should assign to each event? 1 over n. If you want the notion of fairness, every event should be equally likely. So in the uniform model, all events are equally likely. Right? If this is how I assign scores on exams, there would be, I think, a lot of concern with all scores from 0 to 100 equally likely. Right? I am hoping that this will be a highly biased distribution concentrated around 98, 99. Right? Because then it's a lot less time for me to grade. Right? So in practice, we're not going to have all the events equally likely. But if we do, the analysis is frequently a lot easier. What do you think the probability of the set containing omega 1 and omega 3 is? What should that be? I'm sorry? In the uniform model, 2 over n. But I'm not going to put myself with the uniform model. So what should that be in the general case?
Probability of omega 1.
So it should be the probability of omega 1 plus the probability of omega 3. The probability of a union of disjoint sets is the sum of the probabilities. So the probability of A union B is the probability of A plus the probability of B if A intersect B is empty. Why do I have to put A intersect B as empty? Yes. Yeah, I mean, let's take the ridiculous case where B equals A. Then I would have the probability of A is the probability of A plus the probability of A. So clearly there's going to be some difficulties if A and B have things in common. But the idea is if A and B are disjoint, the probability of A and added to the probability of B should be the probability of A union B. So you should read union as either A happens or B happens or both. So in mathematics is the inclusive or versus the exclusive or. We tend to use the inclusive or. So A union B means either A or B. Both could happen. Okay? When I was a freshman, I found out 2 weeks into my spring semester that one of the classes I took, my A- didn't count. I was on, all of a sudden, bad academic standing. I had to quickly put on a class to not be kicked out of Yale. And so I quickly threw in a philosophy of logic class, because I was not really worried about walking in 2 weeks into a philosophy of logic class. 50% of the first exam had 10 statements, P and Q implies not P or not Q. And the instructions said, state which of the following are true or false. So being a smartass, what did I notice? They're all true or false. The teacher slipped up. And I debated writing down, but once you're already hauled before the honor committee, you don't really want to risk going back again. The teacher said she would have flunked me, which I don't really think is justified because it was a logic. I could understand a history professor flunking me for a stunt like that. But she used the wrong or. Know which or you're using. Here, we are using A union B. That means either A or B happens, or both. Does this seem a reasonable statement? The probability of a union is the sum of the probabilities, as long as the sets are disjoint. All right, let's look at some consequences of this. So if we want to look at some consequences of this, am I still in phase? Yeah, I think I'm still in phase over here. Let's take the interval 0, 1, and I'm going to write this as the union over all x in 0, 1 of the set containing x. So the probability that I take the interval 0, 1, that should just be what? This is my entire outcome space. What should the probability of the outcome space be? 1. And then this should be the same as the sum over all x in 0, 1 of the probability I take the singleton x. Now we'll go back to the suggested uniform model that all of these elements should have the same probability. Well, if they all have the same probability, there's two options. Either it's 0 or it's not 0. If it's 0, what is the sum? Well, technically it's infinity times 0. But it does feel a lot like it should be 0. If it's not 0, if it's some positive number, then it's definitely going to be plus infinity. So the only possibility is if each one of these is 0, and now somehow I have to have an infinite sum of zeros. The danger of what's going on here is this is an uncountable sum. And because it's an uncountable sum, that's why something dangerous and something bad is going on. We have to be very careful about how we deal with things. Okay? Infinity times 0, what does this mean? We don't really understand. We only want to work with countably many things. We only want to work with finitely many things when we're trying to figure out what's going on. To go back to Calc 1, what's the derivative of a sum? Sum of the derivatives. So is that true if I have an infinite sum? Is the derivative of an infinite sum the infinite sum of the derivatives? Not always. You should have only seen in Calc 1, if they were kind enough to give you a proof, that this works for finite sums. And the reason I want to do this proof is this illustrates a really good technique which we will use again and again in probability. So derivative of a finite sum is the sum of derivatives. So the proof is going to be by induction. And it's going to use the idea of grouping, and grouping is going to be key through a lot of what we do. If I have the derivative of a sum of two functions you should have proved that that's the sum of the two derivatives. If I now give you a sum of three functions, how should I view the sum of three functions? So it should be, I should view it as f plus g plus h. Now I have a sum of two functions. Because I have a sum of two functions, I can now apply the rule from before. This is now going to be f plus g prime plus h prime. And so I'm being very careful to only use what I've proved. The derivative of a sum of two functions is the sum of the two derivatives. Now what's the derivative of f plus g? F prime plus g prime. And I just use the rule again. And I get f prime plus g prime plus h prime. And I put a little box here to indicate we've reached the end of the proof. So this is the QED symbol. So this gives you a little bit of a sense of how we have to be careful as we go through things. We never proved that the sum, if we have an infinite sum, the derivative of the infinite sum is the sum of the derivatives. We technically only did this in a finite case. In analysis, so much of the difficulty is dealing with the infinite. And this is where, when you take a class like real analysis, you hopefully get very skilled at dealing with those infinities. I wanted you just enough to give you a sense of what's out there and where the difficulties are in making the subject rigorous. I don't want to go through and prove everything from first principles extremely rigorously. We don't want to go back and talk about what does it mean for a set to be finite. But I want you to have some idea of why we have to be careful and why we need to worry about something like this. So what we want to do is we want to talk about what should the probability of A union B be. So we started off with trying to write 0, 1 as an uncountable sum. We had some problems. All right, so now that we have that, let's go back to, almost got it to swing over. All right, so let's go back and look at the probability of A union B. So if we go to the probability of A union B, we want to say it's the probability of A plus the probability of B if A and B are disjoint. A and B being disjoint is not enough. Now, in this particular case, we will be okay because there's only two sets. So this will be fine. We probably want more than just A union B. What do you think we might want? A union B union C. So if we have a wish list, so if we're going to go for a wish list, we would probably want to have maybe sums of unions of 3 things, 4 things, 5 things, and maybe the probability of the union I goes from 1 to infinity of AI is the sum of the probability of AI I goes from 1 to infinity if we have a disjoint union. So this should be something on our wish list, that the probability of a disjoint union, if it's countable, is the sum of the probabilities. So we need countable union. So what we're leading up to is we're leading up to Kolmogorov's axioms of probability. And we're trying to say, what's reasonable things to want? The probability should be non-negative. They should be at most 1. The probability of the whole space should be 1. The probability of the empty set should be 0. We want something like this. Why do we want something like this? Why is this such a useful thing to have? And we've already used this in the class. Why is something like this so powerful? Yes? Not necessarily an integral here, because we don't have areas under curves. I mean, we could do that later, but right now we don't have areas under curves.
It leads to the proof that A plus A complement is 1 because those two.
So I mean, that is definitely related to the probability A and A complement is 1. But why might you want to write an event as the union of AIs where they're disjoint? Where do we write something like that?
It's easier to consider the probabilities of disjoint subsets than the entire thing.
Yes, let's go back to what's the probability bird beats magic from day 1? Was that day 2? Did you do basketball on day 2? Okay, so on day 2, yesterday, we did Bird and Magic were playing hoops. First one to get a basket wins. And we wanted to calculate what's the probability Bird got the first basket. So we looked at the probability Bird wins on his first shot, on his second shot, on his third shot, on his fourth shot. We're breaking a very complicated event, Bird wins, into infinitely many simpler events. And this is one of the big themes of this course in mathematics in general. You would much rather do a lot of easier problems than one really hard problem. Sometimes you'd rather do infinitely many easier problems than one hard problem. And that's why we want something like this. We want to reduce these very hard, complicated problems to something a lot simpler. Let's go back to this, the probability of A union B. What if we don't have that A and B are disjoint? So, if A and B are disjoint, we know what the answer is. But in general, do not assume A intersect B is empty. What is the probability of A union B?
You would do the same probability of A plus probability of B, but you subtract out the intersection.
Good. So the formula would be we take what we have before and we subtract off the intersection. What I want to do is I want to talk about how you would get to that formula. So again, a lot of times in math courses, the material is presented very straightforward, with no sense of discovery, no sense of the paths people went on. It's just, oh, here's a theorem, here's the proof. How do people come to this? How do people come to decide what they should be looking at? The probability of A union B, this should be a function of various objects. What should it depend on? Depends on the following. What's one thing that this should depend on? Probably probability of A. Can't prove it, but it seems really likely. What else? Probability of B. What else? Probability of A intersect B. And it should be symmetric in 1 and 2. And the reason is the probability of A union B is also the probability of B union A. So whatever formula I get, if I change the rows of A and B, I should get the same answer. So what you can do now is you can start looking at special cases and try to figure out what the answer might be. And again, to me, that's far more valuable than just directly proving this. I can directly prove this, but I want to give you a sense of why this is a sense of discovery. So you could start looking at special cases. What would be a really good special case to look at? Who can give me a good special case?
Probability of both A and B are 0.
So that's a little bit too special. So just back up a little bit. Just make it just B. So let's take B is empty. If B is empty, what's the probability of A union B? So now we know it has to be probability of A. And then, of course, we could also then take, for the second one, we could take A is empty. And that gives us the probability of A union B is the probability of A. This gives us the probability of A union B is the probability of B. And we know our formula is symmetric, so we're beginning to see it should be related to probability of A plus B, plus the probability of B. We could also take A and B disjoint, in which case A intersect B is empty. The hard part is then seeing what happens, how are they related. So you could maybe guess, maybe it's the probability of A plus the probability of B minus some constant times the probability of A intersect B. And then is there a constant that would work? There's an easy value to take to figure out what that constant would be if that constant exists. Would be a good case to taste? Yes. Yeah. If A equals B, you get the probability of A plus the probability of A minus C times the probability of A is the probability of A. that would tell you if this relationship works, the only way it can work is if c equals 1. So again, what I want you to be able to do is I want you to be able to sniff out what the formulas are without doing the detailed calculations. And then have some idea of what you're trying to prove. The real world sadly does not come with the answer key. It does not come with the back of the book where you have an idea of what the formula is supposed to be. You have to try to figure out what you're trying to prove. You look at special cases. You analyze the hell out of those special cases. And you try to deduce the general result. What's the last problem on this week's homework assignment? Anybody remember? It's prove the product rule, right? So you should hopefully remember the product rule from Calc 1, right? What's the derivative of a product? Product of the derivatives, right? No, right? So we have a wish list for probability. One of the nice things about probability over calculus is our wish list is for the most part satisfied. You know, we have to be a little bit careful. All right, if I want a probability of a union is the sum of the probabilities, they have to be disjoint. Well, that seems reasonable. And it has to be countable, not uncountable. You know, I'm already working with infinities. I'm fine restricting myself to countable infinities. These are not severe restrictions on us. If you were to write the laws of calculus, would you choose the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second? Is this what you would have chosen? I won't even get into the quotient rule. Would you have set up calculus this way? If you were to set up calculus, how would you have chosen to make the derivative of a product? Product of the derivatives, right? If you had to choose, this seems like a really nice way to start. How many of you remember the proof of the derivative of a product? Well, if not, that's what the first homework problem is for, is to look that up. What I want to do is I want to show you how you could guess the formula. Imagine you've never seen the derivative of a product, and you want to try to figure out what should the derivative of a product be. So we're going to let a of x equal f of x, g of x. What is a prime of x? What do you think a prime of x should depend on? It should depend on f and g. What else? On f, on g, anything else? Probably f prime and g prime. Do you think it should depend on the second derivatives? Hopefully not. Hopefully just on f, g, f prime, and g prime. So what we can do is we can take some special cases. What's a function we can differentiate fairly easily? X, or x squared, or x cubed. What we could do is we could take f of x is x to the n, g of x is x to the m, and then a of x is x to the n plus m. Why would I do this? Well, I can calculate all the derivatives. F prime of x is n x to the n minus 1. G prime of x is m x to the m minus 1. And a prime of x is n plus m. I'll write it down over here. A prime of x is n plus m x to the n plus m minus 1. This now suggests the product rule. I've got to get an x to the n plus m minus 1. Looking at these quantities, I see two ways to get an x to the n plus m minus 1. I can take f and I can multiply by g prime. I can take f prime and I can multiply by g. And I notice if I add those together, I will get this formula. So we notice f prime of x times g of x plus f of x g prime of x equals this. Is this a proof? No, but it gives you an idea of what to try to prove for the product rule, by looking at one special case. Now the question is, are there any other special cases you can do? I am teaching complex analysis right now. It is dangerous to ask people in complex analysis if they remember anything from Calc 3. Integrating along curves and stuff like that. What does it mean for a function of several variables to be different? Dangerous to ask that. I'm guessing a corresponding danger here would be trigonometry. Do people remember all their trig identities? Some of them. So if you remember trig identities, you could possibly do something here. If I give you like sine of x times cosine of x, I can write that as sine of 2x. Or maybe 1/2 sine of 2x. And then maybe I could use something like that to have another non-trivial case and try to support a claim like this. So in terms of how you sniff out formulas, I really want to emphasize mining examples. Okay? You can read details in books. You can go through and you can follow the book as to how it explains why this is true. What you want to get to the point is you want to get to the point where you can create something new, where you can figure out what might be the relationship that should hold. So for today, we saw a lot of the beginnings of probability. We saw a little bit of the language we're going to need, and in particular the language we're not going to use, what we're going to avoid. We saw a little bit of our wish list, and we saw a little bit of why we can't set our sights too high. If we want too much to be true, there's danger. We saw the problem when we tried to split the interval 0, 1 as to an uncountable union. So the key word for us is we're going to look at countable things. We believe that our laws of probability should allow us to have the probability of a countable disjoint union is the sum of the probabilities. And then what we'll do in the next class is we'll do the tree diagram, we'll do Kolmogorov's laws of probability, the axioms of probability, and start really going into the detail for chapter 2. I'm not going to go that much into the sigma algebras and stuff like that. If you want to see that, I think it's section 2.6 of the book, or talk to me. I don't want to go into that in class. All right, have a good day, and for the seniors, I will probably be seeing you